Okay, so we don't have anyone in the center. Yeah. So now it's 5 minutes past 3. I think we will go ahead and start, Rathul. Is that fine?
Yeah, fine.
Yeah. Today we have Rathul, Nath, Raveendran talking about what happened before the Big Bang. I'm myself curious. What's the definition of Big Bang? If he says it's before, so that should be nice. And he's from Indian Association for the Cultivation of Science in Calcutta. He graduated from Madhubali College in Thalassery, and then he did his PhD from Math Science, correct, brother?
Yes.
Yeah, from Institute of Mathematical Science in Chennai, and now he's a postdoctoral fellow in Indian Association for the Cultivation of Science. Thanks, Rathul, for choosing a really nice topic. So I look forward to the talk. Please welcome.
Okay. Yeah. So thank you, Shajesh, for giving me the opportunity to talk about cosmology and specifically what happened before the Big Bang. So can I change my language to Malayalam? Is that okay?
Yes.
I mean, I can use.
I think we have Prachi and Bipan who don't understand Malayalam. So as far as you speak in both languages, that's good, I think. Yeah.
Okay, so I will try. Okay, so thank you, Sajesh. So shall I start?
Yes, please go ahead.
Okay, so what happened before the Big Bang? Okay, ഇത് പലരും കേട്ടിട്ടുണ്ടാവും ഈ ബിഗ് ബാങ് എന്ന് പറയുന്നത് വളരെ പോപ്പുലർ സയൻസിലോ അല്ലെങ്കിൽ മറ്റ് പോപ്പുലർ ബുക്സിലൊക്കെ വി ഓൾറെഡി heard about this, the word Big Bang, right? I mean, this is a kind of a fancy word. So actually, what is this Big Bang? I should mention about before starting the talk. It's actually a bad nomenclature. Like there is a theory called hot Big Bang theory or hot Big Bang model that deals with the origin and evolution of universe, as you know. But അതൊരു നല്ല ഒരു നെയിം അല്ല ഒരു ബിഗ് ബാങ് തിയറി എന്ന് പറയുന്നത്. അത് ആക്ച്വലി ഈ ബിഗ് ബാങ് തിയറിയെ അല്ലെങ്കിൽ ആ ഒരു തിയറി മുന്നോട്ട് വെക്കുന്ന ഒരു മോഡൽ, യൂണിവേഴ്സിന്റെ മോഡൽ, അല്ലെങ്കിൽ യൂണിവേഴ്സ് എങ്ങനെ ഉണ്ടായി, വാട്ട് ഈസ് ദ ഒറിജിൻ ഓഫ് ദി യൂണിവേഴ്സ് ആൻഡ് ഹൗ ഇറ്റ് ഇവോൾവ് ആൻഡ് വാട്ട് ഈസ് ദ സ്ട്രക്ചർ ഓഫ് ദി യൂണിവേഴ്സ്. അതാണ് ഈ ഹോട്ട് ബിഗ് ബാങ് മോഡൽ മുന്നോട്ട് വെക്കുന്ന ഒരു മോഡൽ എന്ന് പറയുന്നത്. അപ്പോൾ ആ തിയറിക്ക് ആ തിയറിയെ കളിയാക്കിക്കൊണ്ട് ആക്ച്വലി അതിനെ എതിർ സൈഡിൽ നിൽക്കുന്ന ഒരു കൂട്ടം ആൾക്കാർ, അല്ലെങ്കിൽ എന്താ പറയുക, വേറെ മോഡലുകളുമായിട്ടുള്ള ഒരു കൂട്ടം ആൾക്കാർ കളിയാക്കി വിളിച്ചൊരു പേരാണ് ഈ ബിഗ് ബാങ് എന്ന് പറയുന്നത്. ആക്ച്വലി അവിടെ ഒരു ബിഗ് ബാങ് എന്ന് പറയുന്ന ഒരു ഇവന്റ് ഇല്ല ആ ഒരു തിയറിയിൽ. അപ്പൊ പിന്നെ വാട്ട് ഹാപ്പൻ ബിഫോർ ദ ബിഗ് ബാങ് എന്ന് പറയുന്നത് ഇറ്റ്സ് എ യൂസ്ലെസ്, അല്ലെങ്കിൽ ഒരു യൂസ്ലെസ് ക്വസ്റ്റ്യൻ ആണെന്ന് പറയാം. പിന്നെ ഇയാൾ എന്ത് ടോപ്പിക്കാണ് എടുത്തിട്ട് വന്നിട്ടുള്ളതെന്ന് ചോദിച്ചു കഴിഞ്ഞാൽ, ഓക്കെ, we will understand, like when we move on we will get to know what happened. I mean, we can define some event, Big Bang, like whatever we call in the theory. There is a event, but that is not actually a Big Bang. It's some kind of a expansion of the space or some okay, in the when we move on we will understand what exactly mean by Big Bang. Okay, so yeah, so that is about Big Bang. Okay, so before actually talking about this model of our universe, we should know about what we are dealing with, what scales we use in our when we model our universe, right? I mean, we know already this in our daily life. We deal with kilometers or meters or that level of, or that kind of scales for the distance, right? But when we talk about cosmology or astrophysical objects, then we cannot use this kind of scales, right? I mean, we have to go beyond, right? I mean, we know that almost size of the Earth is what the radius of the Earth is around 6,000 kilometers. Or yeah, 6,000 kilometers, as I remember. Please correct me if I am wrong. So that is the size of the or radius of the Earth, right? I mean, and കുറച്ചുകൂടെ എന്താ പറയാ വലിയൊരു യൂണിവേഴ്സിനെ അല്ലെങ്കിൽ വലിയൊരു സൈസ് കൺസിഡർ ചെയ്യുമ്പോൾ നമുക്ക് കൺസിഡർ ചെയ്യാൻ പറ്റുന്ന ഒരു സൈസ് എന്ന് പറയുന്നത് അല്ലെങ്കിൽ ഒരു ഡിസ്റ്റൻസ് എന്ന് പറയുന്നത് ഫ്രം എർത്ത് ടു സൺ. What is the distance between Earth to Sun? It's around 150 million kilometers, right? I mean, there are lots of zeros in there, 6 zeros after 150. So after that, or when we consider even beyond that scale, we cannot use these standard scales like kilometers or meters or feet or so we have to consider some other scale. So usually in cosmology or in astrophysics we use either light year, but that is not actually the uh, scientific scale I should say, but what we use is the parsec. Okay, so one parsec is basically like around 3.26 light year. Okay, so it's almost around 10 to the power 15 kilometers. I think you know about this kind of writing. 10 to the power 15 basically means after 10 there is a, what, after 1 there is a 15 zeros. So the one light year is basically 10 to the power 15 kilometers, right? So then the one parsec is basically almost the same, 10 to the power 15 kilometers. So that is actually the distance between, or almost distance between the sun and the nearest star, like after the sun. So that is Alpha Centauri. That's around 1 parsec distance. So that is the distance that's almost equal to 1 parsec. Then if you go even beyond, like if you go like if you know about the star Betelgeuse, it's basically if you are if you know the constellation, I don't know whether you people are aware of it. There is a constellation called Orion. In that Orion constellation, there's a star in the shoulder of that Orion. മലയാളത്തിൽ വേട്ടക്കാരൻ എന്ന് പറയും. അപ്പോൾ ഷോൾഡർ വേട്ടക്കാരന്റെ ഷോൾഡറിലുള്ള ഒരു സ്റ്റാർ ആണ് ഈ ബീറ്റിലീസ് എന്ന് പറയുന്നത്. അത് ആക്ച്വലി മലയാളത്തിൽ തിരുവാതിര നക്ഷത്രം എന്ന് പറയും. ഇറ്റ്സ് ഓൾമോസ്റ്റ് അറൌണ്ട് 200 PC. അപ്പോൾ ഇവിടെ കേൾക്കുന്ന പലരുടെയും ചിലപ്പോൾ നക്ഷത്രം ബേർത്ത് സ്റ്റാർ ആയിരിക്കും ഈ തിരുവാതിര എന്ന് പറയുന്നത്. അപ്പോൾ ഏതാണ്ട് ഒരു 200 PC ഡിസ്റ്റൻസിലാണ് ആ ഒരു സ്റ്റാർ ഉള്ളത്. 200 PC എന്ന് പറയുമ്പോൾ വീണ്ടും 200 times 10 to the 15 kilometers. So that's a distance from Earth to the Tiruvadira star or Tiruvadira nakshatra. Okay, so I'm just trying to give you some feeling of the distance, but when we talk about cosmology or astrophysics. Okay, so we are coming to the scale of distance when we hello. Yeah, so when we talk about this what scales we deals in cosmology, that's what I am going to talk about. So this is a distance between the 200 parsec or 200 times 10 to the 15 kilometers. That is a scale, that is a distance between the Earth and Betelgeuse. And if you some of you already know that the distance of distance from the center of galaxy, our galaxy, it's Milky Way, from the center of the galaxy to the sun is basically 8 kiloparsec, right? I mean, kilo, you know, right? It's 10 to the 3. So 8 10 to the 3 parsec, again 8 into 10 to the 3 into 10 to the 15 kilometers, right? I mean, it's very large distance, And also some of you already know that our nearest galaxy is Andromeda galaxy. It's around 1 megaparsec distant from our galaxy. Okay, so here we start our scale of cosmology. Okay, So we deal with, in cosmology, we deal with 1 MPC and beyond. MPC basically means megaparsec. Okay, megaparsec basically means hours, 10 to the 6 parsec, and parsec is basically 10 to the 15 kilometers. So what is you can imagine, or you can calculate that how many zeros are in front of that when you convert the 1 MPC to kilometers, right? It's very large number, right? So that is the scale we deal in cosmology. I think that is clear now. Okay, so any questions? I think nobody has questions. Okay, that is the scale we start in cosmology. And
question. I was wondering, there are how many galaxies in our universe?
That we don't know.
We don't know.
Billions. When you listen this Carl Sagan's lectures, and he used to say that billions of galaxies and stars. So we don't know actually. There are many, and there is a size for actually observable universe, which is 10 to the 4 megaparsec. Okay, so we cannot see beyond that. Beyond that distance, because as you I don't know how many of you know about special relativity, and there is a limit for our there is a limit for our observable universe or observable distance, because the signals cannot travel more than, sorry,
I think that was just a disturbance. Yeah.
Okay. So yeah,
I also have a related question. So if the nearest galaxy, Andromeda, is about 1 megaparsec, is it a general distance between the two galaxies? Or
sorry, what do you mean by
like average distance between the two galaxies is like kind
it's
of
almost, yeah, it's almost from the center of Milky Way to the center of Andromeda. It's almost, I mean, it's around 8 kpc, like 800 kpc, 800 kiloparsec, but I just rounded and say 1 mpc.
Yeah, that's okay. Like I was just trying to think in terms of like how far, like you said, nearest star is 1 parsec and nearest galaxy is about 1 megaparsec. So is it like an average distance between galaxies in general, or like
in general? Okay. Yeah, that is the average distance. Yeah, we can say in that way. Yes.
But then can we not take the volume of the observable universe and say that it is about 10 raised to 12 galaxies? Is that a bad estimate?
I mean, there are voids, like it's not, yeah, we can say in that way, because there are voids in the universe, but there are, and when you go beyond, say, 100 megaparsec or so, then you will see that the universe is almost homogeneous. So if you consider from 100 megaparsec to 10 to the 4 megaparsec and consider that as a volume, and then see how many then you do the same calculation, then you may get how many galaxies there, because in that range the universe is almost homogeneous. Then you can apply that calculation there. Okay. Yeah, okay. I mean, maybe you are correct. I don't know exactly is that the number of galaxies, but in my opinion, after 100 megaparsec, you can apply that calculation and see. After 100 megaparsec. Yeah.
And how do we know the size of the observable universe?
Okay, size of the observable universe. This is actually the theoretical prediction. Okay, so like we know that there is a limit for our, I mean, there is a horizon, right? I mean, in from the special relativity or general relativity, we know that the signal cannot propagate faster than the speed of light, right? I mean, then if you just you can just calculate that how much, I mean, how far we can see, right? If you multiply that that the age of the universe with that number c, you get almost, it's not exactly, you get almost 10 to the 4 mpc.
But how do we know the age of the universe?
Okay, that we have to calculate from the theory, and also from the observation, in the sense we have to know what are the matter present in the universe, matter present in the universe. Then using our hot Big Bang model and using Einstein's equations, we can get the age of the universe.
Got it. But there is a lot of consistency between various measurements, and we know that it's reasonable.
Exactly.
Yeah. Nice.
So I think that is clear. So the next is so I think you almost understood what are the distance scales we use in the cosmology. It is around 1 MPC to 10 to the 4 MPC. And so now I'm going to talk about what exactly mean by cosmology. Okay, cosmology actually, we can use Newtonian theory of gravity in our calculations of daily life, like when we deal with the when we deal with the physics of very weak gravity, like in the gravity that is how can I say, it is when we talk about the mechanisms, like, or the physical things, or physical, I mean, the I don't know, something we calculate, like suppose a ball or something is falling towards the earth, how we what is the expression due to gravity, or what is the physics of that, then we can use the Newtonian theory of gravity. But when we go beyond that, even for the solar system, you can use the Newtonian gravity, but you need for some corrections from some modified theory of gravity, and you have to modify the theory of gravity to get the correct estimate of some of the planets, the correct estimate of the physics of some of the what should I say, the physics of that. Okay, so I should be more precise. I don't know, because I'm just a little worried about what is the audience like. Should I describe in detail, or
I think
Detail
what
always
you can
helps.
do, no, what you can actually do is like basically describe something in simple terms and then move on. Like not too much detail, but just some little explanation. So for example, Newtonian gravity, you can say that two massive objects like interactions, something like that. Thanks.
Okay. So then I will do that. So as I said, the Newtonian gravity is applicable for weak gravity limit, in the sense in our daily life, or in the solar system, we can use the Newtonian gravity. But when we go beyond, like if you find a system where the mass is very large, or like if you want to study the physics of black hole, or the for very massive system, then you have to modify the Newtonian gravity, or you have to use a more generalized theorem of gravity, which is basically the general theory of relativity. So in cosmology, actually, we need this general theory of relativity to describe our system. Okay, so I don't know how many of you know about this general theory of relativity. As I said, it's a modification of Newtonian theory, but there are more. Like in Newtonian theory of relativity, the two masses attracts always, but in general theory of relativity, there can be repulsion. Okay, and the Newtonian theory of gravity, you can say that it is something instantaneous. The force of attraction is something instantaneous, and general theory of relativity is actually in the general theory of relativity incorporates a special theory also. So there is a time, there is a time for the propagation of this Okay, I am not going to the detail. Just leave it. So general theory of relativity is something little more complicated, and we need this general theory of relativity to study the cosmology. Okay, and not only that, when you go even towards the origin of the universe, okay, I will talk more about this origin of the universe later. So when we go even towards the origin of the universe, then you need even more complicated theory like quantum field theory. So in cosmology, we deal with general theory of relativity and quantum field theory. This is what I want to say. Okay, I think this is clear. Any question?
So question. So if we want to understand the interaction between Andromeda and our galaxy, do we need to take care of general relativity?
Actually, in some sense, yes, because it
Really?
depends upon what you are studying, right? It depends upon what you are studying. In okay, if you want to study even in our Milky Way galaxy, there is a supermassive black hole in the center, right? And if you want to study the orbits of stars very near to the center of our galaxy, you need general theory of relativity. So it is not even between the two galaxies, but even inside our galaxy, in some cases, we need GR, general theory of relativity.
Yeah, but that's why I said two separate galaxies which are relatively far away, like 100 parsecs. So,
Yes.
or 100
Yeah.
kilometers.
So there
Still
also,
then,
yeah, I mean, it depends what you are studying. So what physics you are going to study between these two galaxies. These two galaxies are far apart, and okay, so these are not interacting, right? I mean, there is nothing happening in between them. It's not interacting, but when the universe expands, these two are going far. That is
correct.
true. So that is actually the result of general theory of relativity. It is not like these two galaxies are interacting, but the background space is expanding. That is actually the result of general theory of relativity. So general theory of relativity works there, but in the background. So we need GR. You understood? So there is no interaction. To study the interaction between these two, uh, I mean, there is no interaction to study there. But these two are going far. I mean, the far apart, and for to know the the relative expansion rate or something, you need GR.
Correct.
Okay, I think that is clear.
Yeah.
Is that
think
clear,
so.
Sajesh?
Yeah. Yes, it is. Yeah.
Okay.
Thanks.
Okay. So yeah. So yeah, please ask questions. Otherwise, I don't know how detailed I should go, and so if you ask questions, it may be helpful for me. Yeah.
Okay, great. So maybe I can tell, maybe we will ask questions, and if necessary, you can continue next time also. Maybe that could be the point we can make, because I'm afraid that if we ask too many questions, your talk will.
I think it's okay. I mean, then only I can get the feeling of how, because it's a kind of public
Correct.
talk, and I don't want to just describe and go, because I want somebody to appreciate what I am doing.
So
So
I have a question then.
okay,
I
you can
don't
ask as many
understand how
questions, and
interaction. I don't understand how interactions is the same as expansion of metric or space.
okay, I am not saying that interaction is same as expansion of space in the background. What I am trying to say, uh, there is a these two galaxies are moving away. Not like it's not moving very fast, or it's very slow expansion. Slow expansion in the background. And but I'm not saying these two are interacting directly, right? I mean, interaction through the gravitational force or anything, but these two are moving. It is because of the background expansion of the space. I don't know. Can you does it answer the question?
Okay. Can I make a comment?
I think
Yeah.
yes, Rishi is having something. Yes.
Hi. So actually, I don't know, but so perhaps I think what the speaker is trying to say is that this expansion is a consequence of you put a cosmological constant term in the Einstein's equation, right?
Yes.
And in that sense, it will modify the metric.
Yes.
So it's also a form of the interaction. So the
Oh.
I have a question then. I think all this can be explained even without G, right? I mean, of course, repulsion we cannot, but I thought we have not reached there. We are just currently talking about Big Bang, right? We are not talking about
no, but he's talking about the expansion here, right? He's saying that
since
expansion.
so since Shajesh mentioned about this question, I just jumped into the expansion. That's all.
But not the acceleration. Like expansion doesn't require the constant.
The acceleration.
Right? Acceleration of the
Yeah, the acceleration, of course, the acceleration.
Yeah,
the currently it is.
Yeah, how is the expansion and interaction related? That's my question.
It is not related. It is not related.
Okay.
I mean, in the sense, the interaction can decrease the intensity of this whatever the result due to the expansion, right? I mean, the interaction basically the attractive
slow down
attractive force between the two galaxies, right? So that interaction, that's why we are like the entire space is expanding. So, but we don't see that the Earth is becoming larger and larger because these the old masses are like it's attracted towards the center of the Earth, right? And it's because of an interaction between the masses, right? Or the attractive force between the masses, right? So the interaction between these masses, the attractive force between these masses can reduce or slow down the expansion, or completely can stop the expansion within that range. That's why we don't see expansion or the expansion of the Earth or any massive objects or the galaxies, because they are attracted towards the center because of this attractive force of gravity.
So maybe I have a question again. So in this what is this ideal gas law, we will always assume that the interaction between the atoms is negligible. In this, do we say that the two galaxies or two masses in this expansion metric, that they are not interacting with each other? It is only the expansion that is taking care of this whole phenomena. Is that an assumption made that interactions between the particles are neglected between the galaxies?
No, we should take care of the interaction. I'm not saying that the interaction between these two are negligible, but if you consider the cosmology, actually this Milky Way and all this Andromeda, and there are some other galaxies, these are all kind of in a globular cluster, okay? And these galaxies are actually attracted towards this center of this globular cluster. I mean, these masses are interacting each other. Okay, so it is actually like a solar system. These these galaxies in this globular cluster. So there is an interaction. So when we consider the cosmology, this interaction doesn't matter. So you understood, there is an expansion in the background. Maybe I didn't communicate properly. There is an expansion in the background, but these galaxies are attracted towards the center of globular clusters, or these the galaxies are interact with each other, and it is somehow formed a system. So it is I mean it doesn't what, participate in the expansion of the universe.
So I
That
have a
happens.
question. So this expansion is actually, we are not really trying to explain the expansion, right? Because expansion is the initial condition that that's what the Big Bang, started with. So the expansion is the consequence of the explosion that happened at the Big Bang, and things started moving away. Now, suppose if there is no such thing as a cosmological constant or dark energy or whatever, then of course, then the effect of matter would eventually slow it down, right? That's when we try to understand things in terms of the geometry, how the geometry is shaped by the presence and distribution of the matter, right?
Yes.
So expansion itself, we are not really trying to explain, right? I mean, it's not really, we are not really, putting forward a dynamical cause for expansion. Am I right? It's the initial condition of the Big Bang.
Not actually. The expansion is due to the matter content in the universe. So that makes the expansion, right? I mean, there are solutions in the Einstein's equations. When you put the matter content in the Einstein's equations, you get an expanding solution and also in contracting solution. Okay, whether it is expansion or contraction, that actually depends upon the initial condition.
But suppose if we say that I don't have this dark energy kind of term or a cosmological constant kind of term. Okay. Then how do I get the expansion?
Because
I mean, if you don't assume that things were like thrown apart in the very beginning, okay, and there is the initial push given to all these things. If you don't take that into account, then purely based on the modification of geometry due to presence of matter, how do we explain the expansion?
That is true. But it doesn't. It's a solution. Like if you put the radiation or matter in the Einstein's equation, you get some solution, right? I mean, but that solution allows expanding universe. Whether it can be, if it is dark energy, then it is an accelerated expansion. But if it's a matter, then it's a kind of decelerating expansion. But that allows the expanding universe. It also allows like stationary universe, as you said. That depends upon the initial condition.
Then I want to understand that okay, I can understand how stress energy tensor can modify the metric and give rise to concentrations of matter. How do I understand then the expansion purely based on, if I don't put in any term which gives rise to acceleration, then how do I understand the acceleration expansion physically?
Okay, so in the Einstein's equation, there is a geometry part and there is a matter part, right?
Yeah.
So in the metric, we have this scale factor, which basically is a function of time, and that actually says how what is the size of the universe, and the derivative of scale factor gives what is the rate of expansion of the universe, right? Once you put this geometry in the Einstein's equation and also stress energy tensor in the Einstein's equation, you get equations that allows expansion, contraction, all these things. That depends upon the depends upon the matter content of the universe, or the stress energy tensor of the matter in the universe.
Okay.
And by giving the initial conditions and actually even without the initial condition, you can say that whether the universe is in what rate the universe is expanding. If it is matter, as I remember, the expansion rate is something like that I can say in terms of Hubble parameter, around Hubble parameter is 1 over a cube, in the sense when the universe expands, you can say just decelerates. So it's if the universe contains matter, then it expands, and the energy density of the universe goes as 1 over a to the power 3. A is a scale factor. So this is how it expands. I don't know whether I answered the question correctly, but that is in that is more detailed.
Yeah, I think we can move on from.
Okay. What I want to say. Okay, can I say for the other audience for
Yeah,
Malayalam?
sure. Yeah,
Okay.
sure.
Because I
Please feel free. Yeah.
people also. Yeah. Actually, എന്താ ഞങ്ങൾ ഇപ്പോൾ ഡിസ്കസ് ചെയ്തതെന്ന് വെച്ച് കഴിഞ്ഞാല് നമ്മുടെ യൂണിവേഴ്സില് ഡിഫറെന്റ് ടൈപ്സ് ഓഫ് മാറ്റർ ഉണ്ടെന്ന് പറയാം. അതായത് റേഡിയേഷൻ, സാധാ നമ്മുടെ ഭൂമിയിലൊക്കെ കാണുന്ന പോലത്തെ മാറ്റർ, അതുപോലെ തന്നെ ഒരു ഡാർക്ക് എനർജി എന്ന് പറയുന്നത്, ഇതൊക്കെ അടുത്ത സ്ലൈഡുകളിൽ ഞാൻ പറയാനിരുന്ന കാര്യങ്ങളാണ്. അപ്പൊ ഈ ഒരു മാറ്റർ കണ്ടന്റിനനുസരിച്ചാണ് വെദർ യൂണിവേഴ്സ് എക്സ്പാൻഡ് ചെയ്യുന്നുണ്ടോ ഇല്ലയോ എന്നുള്ള കാര്യങ്ങളൊക്കെ നമുക്ക് പറയാൻ പറ്റുന്നത്. അപ്പൊ അടുത്ത സ്ലൈഡുകളിൽ ഞാനത് കൃത്യമായിട്ട് പറയും. നിങ്ങൾ ഇപ്പൊ ഡിസ്കസ് ചെയ്ത കാര്യങ്ങൾ ഫോളോ ചെയ്തില്ലെങ്കിൽ ജസ്റ്റ് ഒന്ന് പറഞ്ഞു എന്ന് മാത്രമേ ഉള്ളൂ. എന്തായാലും അടുത്ത സ്ലൈഡുകളിൽ ഞാൻ ഈ കാര്യങ്ങളൊക്കെ പറയാം. ഓക്കെ, can I move on?
Yeah.
Okay. Okay, so did I answer your question, Sajesh? I mean the interaction.
Yeah, maybe I can ask once more. Maybe it's just so. Usually, there is a popular picture given about GR, and that is you have a converging well because of a mass. And if there are two such converging wells, there seems to be an interaction, right? Two marbles on an elastic membrane. Right? That's a very, I know it's a very cartoon way of doing it, but that helps. Now,
Yes.
Here we are not talking about that. Here it's an expansion. So is it correct to say that we have only one well where all these particles are there and all these dimples because of these masses is not significant? And this radius of the well itself is increasing, and that's what you mean by expansion of the scale?
Exactly.
Right? Okay.
Yes, exactly.
Okay, I'm good. Okay, great.
So maybe it will be clear in the coming slides. Okay, so this is exactly the answer to your question. Yes. So as I said, when we go beyond this 100 megaparsec, we can see that the universe is almost homogeneous and isotropic. Homogeneous basically means energy density of the universe in different area, different region in the universe are the same. And isotropic basically means that when you look at different directions in the universe, you see the same universe, the same matter content everywhere. So this is observational fact. Okay, so if you add this observational fact in general theory of relativity, you will see that the universe can expand or contract. Okay, this is actually as you know, the general theory of relativity is developed by Einstein, and this idea of the evolution of cosmology, like based on the universe is homogeneous and isotropic on large scales beyond the 100 MPC, is basically developed by or calculated by, or the equations of motion of such universe is calculated by Alexander Friedman, and he argued that the universe can expand or contract because of this these properties, like the universe is homogeneous and isotropic on large scales. Okay, so in 1920s, after the developments of GR and the Friedman equations, George Lemaitre argued that the okay, universe is expanding. If the universe is expanding, then the velocity of stars or galaxies is proportional to the distance of that galaxy from our Earth, or from where we are observing. So this is the idea put forward by George Lemaitre in 1926, and he obtained these equations. Velocity is proportional to the distance to that star or whatever galaxy from there. Then after that, in 1929, Edwin Hubble observed this exactly. Okay, he observed that the velocity of he found some stars in the nearby galaxies and observed the redshift from the galaxies and found the velocity of those stars, and he obtained that observationally the velocity is proportional to the distance from us, a distance of that particular galaxy from us. Okay, so this is called Hubble-Lemaitre law. Okay, this is the basic idea of our hot Big Bang model. Okay, so this is where the hot Big Bang model starts. Okay, I think that I made it clear. Okay, is that okay, Sajesh?
So what is Hubble's law again? So every, in simple words, every star around is moving away from us?
Not exactly. Wherever, okay, so you place an observer in Earth and measure the distance or measure the velocity and distance of that star, then you get this relation, and you go to some other galaxy and do the same calculation, you get exactly the same. So it is not like the stars are moving away from us, but stars are moving each other, or the galaxies are moving each other. Okay.
So here is a question. So we obviously cannot go to another galaxy, right? We only know about our galaxy. So why can't we assume that we are the center of the universe?
So actually, this relation is obtained from the assumption that the universe is homogeneous and isotropic, which means from wherever you see the universe, you see the same universe, so the same homogeneous and isotropic universe. Okay, so theoretically, we can obtain this relation using these cosmological principles.
Yeah, I get that, but we obviously cannot measure this from another galaxy. We only know this from our galaxy, correct?
Yes, that is true.
So is it, or does the Hubble's law or Hubble's observations match with the idea that we are the center of the universe, even though I understand?
Okay, so if you consider only the observations made by Hubble, then you are right. But if you take this Hubble's observation and the cosmological principles, then you cannot say that. Okay. If you take only that observational thing, then you are right.
Okay.
Yeah, but
what about the distance between the two stars? Will that also obey the same thing? Something like that?
Yes.
Yes. I can mute them. Hold on.
Okay. Yes, so that is actually Hubble-Lemaitre. Earlier it was called like Hubble's law, but now it is renamed as Hubble-Lemaitre law, because theoretical prediction actually done by Lemaitre and observational prediction done by Hubble.
I see.
Okay. Yeah. So yeah. Okay. So this is the starting of hot Big Bang model. As I said, hot Big Bang model is actually a bad name. Okay. There is no Big Bang. Okay. This is simply the theory of expansion of the universe. Okay. This theory is basically based on, as I said, GR and cosmological principles, and there are two principles. One is the universe is homogeneous and isotropic, and another is, there are two principles. One is homogeneous, and another is the universe is isotropic. Okay, and also we need quantum field theory when you go back in time and approaches the singularity or very early universe. Okay, so combining these three ideas, we can set up a model for our universe, that is the hot Big Bang model, and also using the observations made by Hubble and also some observations of CMP and all these things that I will come after some slides maybe. Yeah, so according to this theory, as I said, the universe is expanding now, and the galaxies or the stars are moving apart. And according to this theory, when we go back in time, you can assume that these all galaxies and clusters of galaxies or whatever large scale structure we see, these things started from a very hot, dense soup kind of thing. Okay, and
So question.
this, yes.
So you say hot, like this is temperature, right? What do we mean by
Yes.
temperature in this whole theory?
Okay, temperature. Okay, so today, I mean, we know the notion of temperature. I mean, temperature is basically the what the energy, basically the energy of the average energy of the particle content, right? So we know the notion of temperature, and today we know the temperature of whatever we observe. Like there is a spectrum we observe today as cosmic microwave background, and that is actually we can assume that that is the temperature of the universe today. It is around 2.7 Kelvin. That is the average temperature of the universe today. But you can say it's not correct, because I can see the galaxy, it's very hot, and there are the center of sun is, or the sun, it's very hot, but how can you say it's 2.7? But I'm saying in average there is a spectrum of photons that we can detect from the universe, that has a temperature of 2.7 Kelvin. Okay, right. So when that is 2.7 Kelvin, that is the temperature today. So when you go back in time, all this matter come together, and using this radioactive, not black body theorem, and you can get the temperature of the universe, in the sense if the universe is made up of some matter, then you can get the relation between the matter and the temperature, right, from the black body theorem. If you remember, I think the energy density is proportional to T to the power 4 or something, right? That is the black body law or something. I don't remember exactly the name, but something,
so
some relation
is that the black body radiation or the black body curve will be valid even at the time of like, let's say, early Big Bang times. So
yes,
that's an expectation, or that's assumed.
It is also observed as CMB. You can see that the black body, it's exactly the black body radiation.
Correct, and that is pretty old. Yeah, I see.
Yeah. So so when we go back in time, as I said, the universe started as a very hot, dense, some kind of soup, you can say, and that soup contains different kinds of particles, the gauge fields, photons, and everything. That is that's very hot, in the sense we cannot even imagine. We cannot actually imagine the size and the temperature of that hot system. Okay, so it's a kind of but I mean, we cannot do that, so don't try to imagine that. So it's a kind of very hot and very small size thing, a very dense thing. So that is where the universe started. This is actually the hot Big Bang model, uh, which is actually developed from the Einstein's theory of relativity, and there are lots of predictions from this hot Big Bang model, and
Let me see. Okay, go ahead.
oh, yeah, so this is actually the hot Big Bang model. Okay, മലയാളത്തിൽ പറയാം. അതായത് നമ്മുടെ യൂണിവേഴ്സ് ഒരു വളരെ ചെറിയ ഒരു ഡെൻസ് ആയിട്ടുള്ള ഹോട്ട് ആയിട്ടുള്ള ഒരു സിസ്റ്റത്തിൽ സ്റ്റാർട്ട് ചെയ്ത് പിന്നീട് എക്സ്പാൻഡ് ചെയ്യാൻ തുടങ്ങി, എക്സ്പാൻഡ് ചെയ്ത് ഇന്നത്തെ നിലയിലുള്ള യൂണിവേഴ്സ് ആയിട്ട് മാറി. ദിസ് ഈസ് ദ വെരി ബ്രീഫ് ഐഡിയ ഓഫ്, അല്ലെങ്കിൽ ഒരു വളരെ ബ്രീഫ് ആയിട്ടുള്ള ഒരു ഹോട്ട് ബിഗ് ബാങ്ങിന്റെ ഒരു ഐഡിയ ഇങ്ങനെയാണെന്ന് പറയാം. വളരെ ചെറിയൊരു ഡെൻസ് ആയിട്ടുള്ള ഹോട്ട് ആയിട്ടുള്ള ഒരു സൂപ്പിൽ നിന്ന് നമ്മുടെ യൂണിവേഴ്സ് സ്റ്റാർട്ട് ചെയ്യുകയും ഇന്ന് കാണുന്ന തരത്തിലുള്ള വലിയ ഗാലക്സീസും അതുപോലെ തന്നെ നക്ഷത്രങ്ങളും ക്ലസ്റ്റേഴ്സ് ഓഫ് ഗാലക്സീസ് ഒക്കെ ഇതിന്റെ എക്സ്പാൻഷൻ നടക്കുന്നതിലൂടെ ഓരോ സമയത്ത് ഓരോ തരം ഗാലക്സീസും പുതിയ ആറ്റങ്ങളും പുതിയ മോളിക്യൂൾസ് ഒക്കെ ഉണ്ടാവുകയും പുതിയ സ്റ്റാറുകളൊക്കെ ഉണ്ടാവുകയും ചെയ്തു. അതാണ് ഈ ഹോട്ട് ബിഗ് ബാങ് മോഡലിന്റെ ഒരു രത്നച്ചുരുക്കം. ഓക്കെ, I think you got the point. Okay, so yeah, then also we can find out what exactly the age of the universe, as I said, using this GR and cosmological principle. And if you know the content of the universe, then you can basically measure the age of the universe by solving the Friedman equations, and Friedman equations were obtained from the Einstein's equations. So it is actually 13.8 billion years old. Billion is basically how many zeros? Billion, million, billion, 10 to the 12, right? 13.8 times. Yeah, it's 10 to the 9, because billion is 10 to the 6 and then billion, right? Yeah, it's 10 to the 9. Yeah, 13.8 into 10 to the 9 years old, right? So that is the current understanding of the age of the universe. Okay, and also from the observation we know that the universe is almost flat. Okay, it's a okay that അതും മനസ്സിലാക്കാൻ ഇത്തിരി ബുദ്ധിമുട്ടാണ്. കാരണം ഫ്ലാറ്റ് എന്നതുകൊണ്ട് നമുക്കിപ്പോൾ ഒരു ടേബിൾ ഫ്ലാറ്റ് ആണെന്ന് പറയാം. ഒരു 3-dimensional യൂണിവേഴ്സിൽ 2-dimensional ബോഡി ഒരു ഫ്ലാറ്റ് ആണെന്ന് നമുക്ക് ഇമാജിൻ ചെയ്യാൻ പറ്റും. പക്ഷെ യൂണിവേഴ്സ് ഇസ് 3-dimensional ബോഡി, right? How can we imagine that the 3-dimensional body is flat? Then theoretically you can go to 4-dimensional space, and then you will see that the equations of the geometry of the universe obeys obeys some conditions which is valid only in the flat space. That's how we understand the flatness of 3-dimensional body. I think that is clear. Is that clear, Sajesh?
Yeah.
Okay.
I got a message saying that I should let the talk proceed. So
okay. I mean, I can talk about this even next week, or
yeah.
I mean, wherever I can stop, you just told me stop. I can do the things any other time also, because I don't want to go very fast and
correct.
just
no, that's why I took some liberties, but then Prachi pointed out to me that I should not ask too many questions because the talk will slow down too much. Sorry.
Yeah, I mean, I'm feeling this is a kind of discussion, and I don't want to just, I mean, yeah, the name is lecture series, that I understand, but I don't want to give a lecture in the sense. Exactly. I just want to discuss the things and move on.
Yes. So in that sense, so when you say flat, do you mean the space and time is flat, or the space is flat, or what's that mean there?
Okay, the space is flat. That's the
Space
meaning.
is flat. Okay.
It has a spatial geometry.
Flat.
I mean the flat spatial geometry.
And
Yeah.
what do we mean when we say it's made up of radiation and matter, like excluding dark matter and dark energy in the second last sentence? So what is radiation in principle?
Radiation, basically, I mean the relativistic particles, which include photons and other relativistic particles.
But in simple terms, does that mean it has a negative content in some sense? Like, because earlier you made a comment saying that radiation will lead to repulsion, correct? Radiation dominated.
No. Did I say that? Then I was. I'm
Or
wrong.
maybe I got, yeah, okay. So how will you
I
differentiate
mean,
radiation and matter in principle?
okay. Yeah. So the radiation. Okay. So the usual, as you mentioned, that in the ideal gas law, there is a relation between density and pressure, right? Right. So in the case of radiation, if you write the pressure is equal to some quantity times density, then that some quantity is 1/3. That is the definition of radiation. Okay. Matter is basically that quantity is 0. Okay. The pressure is 0. That is the matter, the definition of matter.
Okay.
It can be dark matter, baryonic matter, or not. In cosmology, this is the definition.
Got it.
Yeah. And dark energy, it has pressure is negative. Like pressure is equal to minus rho. That is the definition of dark energy. Yeah. I mean,
would it be very trivialistically, naively speaking, it is because matter has a finite boundary. There is no, like when we think of a field, for example, like a magnet, like radiation has a farther approach than matter. Is that the reason why that pressure is not 0? Or it's just naive way of looking at it? Is it too naive?
I have to think.
Okay.
That I have to think.
Okay. Thanks.
I mean, we can find out the pressure from the distribution function, right? The relativistic, how the relativistic particles are distributed. I mean, it obeys some kind of distribution function. From that, we can obtain that the pressure is what 1/3 times the energy density in average. Something like we can. I
so
think
even
we can
for
derive
neutrinos, you will have the same. I mean, right? For the
Neutrino is also
pressure.
the same. Yes. Yeah.
I was just trying to motivate somehow. Why is that 0 pressure being 0 in an ideal gas law?
Okay. So
myself,
pressure as you if you do the if you do the experiments in lab but we know that the pressure is not 0 for ideal gas, right? And the usual gas of molecules and all, we know it has some pressure. But when we come in the context of cosmology, we consider the pressure is very much small and it's almost equal to 0. Okay, it is not the pressure we talk in the case of molecular, I mean the gas of molecules or these things, but we take it exactly 0. Yeah.
So pressure is in standard thermodynamics defined as change in energy with volume, right? Negative change in energy with volume. So here you said something with density, right? Pressure is proportional to density.
Okay. In Yeah, in cosmology, what we talk about is energy density of all these quantities, because here the system is very large and we cannot talk about the volume of the universe.
Yeah.
Right.
Yes.
So
Yes.
whatever is important is the
Density.
local thing, like the local definition of the energy or pressure. Okay. We cannot consider we don't know what is the volume of universe, and actually we don't need that concept in solving the Einstein's equations and find the evolution of the universe. What we need is the pressure and energy density, all this kind of local things. Okay.
Yeah.
Yes,
So
I think
then, I mean, maybe a comment. So if I were to include the interaction between two galaxies, then this will not be zero, correct? Would I be
yes,
right?
exactly. Yeah, exactly.
Okay.
Then you have to consider the I mean the Boltzmann law and Boltzmann
Right.
equations and how the galaxies are interacting. That's why I mentioned in cosmology we just consider there is no interaction between the stars and galaxies, nothing, and we just put in the Einstein's equations like pressure is zero and solve for the evolution of the universe. If the universe is dominated by matter.
Got it.
Okay. Yeah. So
Thanks.
yeah, so you got that answer now. Okay.
Yes.
I'm happy that. Okay. Yeah. So this is actually, I just want to say that the Big Bang. Okay. So okay, I didn't say about what actually the Big Bang is. So this is actually the old Big Bang model. I mean, old in the sense there is a profound modification after 1980s. Okay, so this is the old Big Bang model before 1980s. Okay, so the Big Bang basically means that the expansion from that very hot, dense soup. Okay, there we this model assumes that the space, time, and everything started from that point. Okay, but that is a finite thing, right? Like if it is a hot, dense, and it contains atoms and relativistic particles and all, then that's a finite thing, right? I mean, the finite finite form of some plasma or whatever, right? So this is the old model of our universe. Okay, so so as I said, there is no Big Bang. I mean, from that hot soup, it just expanded. I mean, the space and this the matter inside that space just expanded. That's all. Okay, so this is just I should mention that this is the old model of our universe. Old in the sense this is true until a point. So we have to see what before this model, or what before this Big Bang point or whatever. Okay.
Can you please clarify again what do you exactly mean by old model and which is no longer true?
Old, yeah. So it is. I'm not saying this is not long. It is not true. I mean, no longer true. What I'm trying to say, we need to modify this. Up to some point, this is true. Up to say after the okay, suppose we have a new model and we just say that model starts from t equal to 0 or the time equal to 0, then this hot Big Bang model starts from 10 to the power minus 12 seconds. So beyond that, or if you go back 10 to the power minus 12 second or 13 second, we cannot apply all these calculations. Okay, so until that point, this hot Big Bang model is correct. Is that clear?
I'm going to say that okay, from 0 to 10 to the power minus 12 second, it is correct.
No, this is not correct
After
for that region. After that,
okay.
it is correct.
Okay.
After that, it is correct. From 10 to the minus 13 second to now, this model is correct.
So when you pose this question that what happened before Big Bang, you are
What I
essentially
mean-
trying to address between 0 to 10 to the minus 12 seconds.
Exactly. So what I mean is what happened before the universe, which was explained by this model of cosmology.
Okay.
Yeah, that's it.
Okay.
So
And
this is the
the reason that it is not applicable, is it because that the space-time was too curved for the calculations to make sense?
actually yes and no. Because this model, as I said, it is starting from a finite space, time, and that space contains some amount of matter, right? So we have to go beyond and see what is the origin of this hot soup, right? We cannot, yeah. So we need what we need some kind of okay, some kind of modification, because from the observation, what we know is the universe is made up of radiation and matter. And if we consider only these two matter, these two kind of content are present in the content present in the universe, then you cannot go beyond this point. Is that clear? Yeah. So we need some modification to see how the universe has begun and how the structures in the universe has begun.
Okay.
Okay.
Thanks. Sir.
Any other questions?
So Rathul, just strategy of the talk. I was wondering how far are you from your talk, and
So
how open are you to break this into two talks or even more?
I mean, I can. Yeah, I mean, I can break. I mean, you can just tell me whenever you want to stop. Yeah.
Maybe you can find somewhere a convenient time and break the talk into two.
Oh, now it's almost over the time.
No, I was thinking. Oh, we started at. I mean, what time am I saying? I'm all confused because I'm in.
Okay, 3. Now I can tell you the time.
So,
It's about 4:15 there.
Oh.
Yeah, so we have crossed 1 hour, right? But what I say is that we can still have some discussion, but find a suitable time. And Prachi, do you think that's better, or?
Okay, so I just introduced hot Big Bang. So what I want to say is what are the evidences of this hot Big Bang, and then I will go to what happened beyond the Big Bang.
Right. Yeah.
Okay. So maybe I can stop it here, and I can just explain in the next lecture. I think one lecture is enough for the rest of the talk.
Okay. Yeah, that sounds good. So maybe I can ask one more question, if that's okay.
Yeah.
Did you? I mean, I'm not sure if you motivated. Like, how do you get the time of 13.8 billion years out of this model?
Okay. So as I said, this Big Bang model is based on Einstein's theory of relativity and cosmological principles. So from these principles and GR, we get some equations of motion of the universe, and also we need some input, like the universe containing radiation and matter. Okay. And also we need how the radiation decays or how the radiation energy density of radiation and matter evolves, but that we get from the Friedman equations itself. So using these ideas or information, we can calculate what is the age of the universe. We know now what is the content of the universe, and use our equations of motion of the universe, which is obtained from GR and cosmological principle. Okay.
Yeah. So here is my question here. So if I understand correct, the scale and the universe we are assuming is for the whole universe, not the observable universe, right? We have presumably the whole space, correct?
Okay, so we cannot talk about the entire universe. What we are talking only about the observable universe.
Okay.
I'm not observable universe. Let me clarify that. Yeah, observable universe.
And that is for us.
Yeah.
And we might be in a very corner of this so-called space-time. And so how can we make any assumption about the density and radiation amount content of our universe just by seeing presumably a local region, because it's observable, right? I mean, light takes finite time. So am I thinking right, or am I surely thinking wrong?
Okay, actually? So we have almost the evidence of this cosmological principle. So wherever you go, you see the same energy density, and so we just assume this is true everywhere.
Oh,
Okay?
yeah, it is
we
density,
cannot,
right? Yeah. Because we have assumed homogeneity and isotropy, and it's only density we have to worry about. Sorry, I think I get my, I got my answer. Yeah, okay. Correct.
Okay, Rathul, one question.
Hmm.
So can we have a situation where universe is homogeneous and not isotropic?
Situation in the sense, in the very early universe, we are, I mean, there are models like it can be homogeneous but not isotropic. The situation, I mean, what do you mean? You mean, is there any evidence of that? Or?
No. I mean, I'm trying to understand if homogeneity would imply isotropy, or it has to be a separate.
No. These are separate. Homogeneity basically.
No, they are separate. They are known to be separate. But I'm trying to understand, from a say purely three-dimensional perspective. So if you have non-isotropy, then it's different in different direction, right?
Exactly.
But would it also not mean that it's not homogeneous then?
That's a good question.
I know that these are generally considered to be two separate requirements, homogeneity and isotropy. But suppose I'm trying to understand how can I visualize a situation which is homogeneous and yet not isotropic?
Homogeneous.
Would it not violate homogeneity if it is not isotropic?
That's a good question. If you see the universe from a different galaxies, and you see it is everywhere it is isotropic, then you can imply that the universe is homogeneous. That implies that the universe is homogeneous. What I mean is, if you find the universe is isotropic from different places, then that implies that homogeneous. But in the opposite way,
homogeneity would require you to see universe from different points, right? It requires that it is same everywhere. Homogeneous means it is same everywhere.
Yes.
Right. If we think of a boundary, maybe like a toroid is, if we are thinking of an inside of a toroid, then I can have a homogeneous situation everywhere, but then it's not isotropic, right? Is that a possible? Maybe not.
Mm,
No,
I
but yeah,
guess
so yeah.
it is described. I mean, one is related to direction and one is related to position, maybe. Like
yes.
you can consider it as a terrain, maybe. Like
No, I that is fine. I understand. What I'm trying to say is that I'm trying to see if a situation where you have homogeneity and not
Not
isotropic.
isotropic. Yeah. Good
I'm
point.
trying to visualize. I mean, they have to be separate because ultimately they are related to the, the conservation of linear momentum and angular momentum, and these are two separate things, right?
Yeah.
So, but I'm trying to visualize a distribution which is homogeneous and not isotropic, and I'm not somehow able to do that.
Actually, that
Yeah,
you
that-
gave the answer, right? A rotating universe. Like a rotating universe at different speeds, let's say, which is not in the same direction, that won't be isotropic because angular momentum is not conserved then. So you answered your own question that isotropy requires angular momentum conservation. I just have to consider a situation where angular momentum is not conserved.
Yeah.
Isn't it?
So, no, but if you you're saying that the universe as a whole is rotating,
Yeah.
and it is
And its axis is changing.
yeah, no, but the point is, what do you mean by rotation of the whole universe? Then when you define for me this whole, I mean, because there is no notion of space or space-time beyond the universe, right?
Yes.
So it's a manifold, that's why when we talk of manifolds, a manifold is a thing by itself. It does not require any embedding in any higher dimensional space. Okay.
Yeah.
So now staying within the manifold, you have to define for me the notion of the rotation of the universe as a whole.
Yeah.
Does it make sense?
So
Yes,
then I
yes,
would
yes.
say if we are agreeing with the manifold thing, then toroid must be an example, right? A toroid where the space is confined only to the inside, space-time is confined only to the inside of a toroid, then it could be homogeneous, but then probably it's not isotropic.
So toroid meaning this Medubada.
Yes, exactly. The Vada, yeah,
Right?
Medubada, yeah.
Yeah, the Medubada, right? Yeah.
Yeah.
So if
Correct.
it is same everywhere inside that toroidal region,
Density could be the same, homogeneous, but then looking inward and outward is different.
no, but again, okay, yeah. So okay, so basically then that means if there is a thing with a boundary,
Yeah,
manifold with a
anything that
boundary,
has a boundary, it will be
boundary
easy to
will
manage.
have perhaps the situation where because
Right.
you have to have a boundary in order to break the different directions, the similarity between different directions. Yeah, maybe perhaps I think that example perhaps serves the purpose. Yeah, I have one more question, Sajesh. Can I ask?
Yeah, please.
Yeah,
I mean,
yeah,
it's
yeah.
all free to ask. I mean, I don't think I'm anchoring.
Yeah. So Rathul,
Yes.
I'm still trying to understand. So you said that you have that it allows the both expansion and I mean, see the possibility is one thing, but how do you understand the physical origin of? See, we all know that suppose if you assume that there are no such thing as vacuum energy and all that, or for the time being you suspend all possibilities of negative pressure, matter with negative pressure. Okay, then how do I understand the expansion other than being an initial state of initial condition? Because suppose I have a soup of matter and energy density, what matter and radiation, that the okay, you're saying that okay, so it's the dynamics between the matter and the radiation which will ultimately dictate the expanding or the contracting solution, right?
Yeah.
Yeah, okay. So
It's just solving the Einstein's equation.
Yeah.
It doesn't.
Okay, no, I get it, sir. Basically, if you have a radiation, basically you have relativistic matter, then it will contribute to the pressure and sort of stop the gravitating effects to coalesce and form structures, right?
Yeah, that's true. Yeah, it just decelerates, that's all, but it doesn't mean that it doesn't cause the expansion, right? It just the universe can. Yeah.
No, so we can. So can we understand this expansion of the universe purely? I mean, so this initial bang, which sort of gave the push for things to expand, is coming purely from the, the equation of state of the matter and radiation in the early universe, right?
Yes. I mean, if
There
you
is
have
no.
already.
Yeah. Okay. Yeah, I think that's a fair explanation.
Actually, even in the early universe, the dark energy was very subdominant. The radiation was the dominant contribution, so there is no negative pressure.
Exactly. Yeah.
So when was the dark energy or this negative pressure requirement for this first realized?
Actually, we didn't know until 1988, right? 1998.
98.
Because,
no, but I was saying,
90.
was there a suggestion for it before that? I know experiments came at that time, but was there a suggestion or even academically, as an academic exercise, was it analyzed before?
Yeah, actually, there was a suggestion.
Einstein himself, right?
Yeah, I mean, there is a yeah, I think the Friedman obtained this de Sitter universe solution first.
Okay.
Because de Sitter basically means it's an accelerated expansion or exponentially expanding universe. So it's actually a theoretical. It's not a prediction, but it's a solution of Einstein's equations. But at that time there was no observational evidence of acceleration, so it's kind of a theoretical model. That's.
In fact, so there is a famous story about Einstein talking about this greatest blunder, right?
Okay, that
because
is
his model was predicting this expansion, and then he put in this cosmological constant to explain a finite universe, right?
Yeah, steady state universe.
Sorry, yes, to explain and then later on it was found that actually it was indeed expanding.
Yeah,
so
that is true.
It dates back to as early days as the, I think, 20s, right?
But I didn't. I don't know whether. I mean, apart from as a theoretical prediction, I mean the theoretical model or the simple model come out from the Einstein's equation, whether it has any validity in the as a cosmological model, like before 1998.
Yeah. I mean, then it was the observational, those things which compelled people to rethink about possibility of putting a.
Yeah, and now we think that it is not actually a constant. There are models like it can vary, and it can, like, it's not just a constant, like p is equal to minus rho. It can be some function of rho, and p can be a function of rho, and it can be some scalar field, may not be a cosmological constant. So yeah, the pressure can change with time or with energy density. Yeah.
So one more maybe, is there, I mean, this might be going into your next part of the lecture, but is there any other candidate to dark energy other than quantum vacuum energy?
Yeah. So there there are, as I said, it can be some scalar field, but we don't know what that scalar field is, but it can be some kind of scalar field and it can mimic the dark energy. So yeah, it's a one solution. Yeah.
Okay. Nice.
So maybe I can go to completely unrelated stuff now. Like
Okay.
you guys are talking physics, that too high level, cosmology. Why there is a need of a starting point?
Why there is a need of a starting point?
Starting
one
point,
thing is
right? T
we
equal to
know
0, you mean?
Yeah, t equal to 0, why there is a need? Why cannot be a t negative something?
yeah, it can be. So maybe that I will talk about in the next session, and I mean the next talk. Yeah, we need, I mean, some kind of, I mean, that is our belief. It started from somewhere, and of course it is an expanding universe. So when you go back in time, is everything come close, and we expect that there should be some point where everything goes into singularity, but it may not be the case. Yeah.
So probably related to this. Yeah, go ahead. Complete your.
I mean, it can be kind of there is a contracting phase before the Big Bang and then expands and again it contracts. It can be a cyclic universe, and our universe is a part of one of the cycles, something like that. Yeah, it's possible, and it's
In fact,
eventually.
yeah, there are papers by Roger Penrose.
Yes, he has a model conformal cyclic universe, and that is basically the one model of cyclic universe. So he's just saying that there can be contracting phase before the expanding phase of our universe. Okay, and he's predicting some kind of observation, some spot in the cosmic microwave background radiation, and that spot, some kind of hot spot or void or whatever. So that is the he's saying that is the evidence of a existence of contracting phase. Yeah.
I just want to touch upon the Prachi's question about. See, I mean, it's a very complex question, but the moment you talk about time, I mean, you cannot just talk about the time alone, right? I mean, time and space are very non-trivially interwoven in both special and general relativity. So this whole question of what is time begs us to know what is the nature of space-time, and I think that's because gravity, all along we have been only talking about the classical gravity, right? We do not really have a quantum theory for gravity. I mean, there are, of course, various proposals. There's two famous streams, right? I mean, the string theoretic approach, where you have a particle of spin 2, the excitation of the strings. And then you have this approach of people doing loop quantum gravity, where they quantize the very arena of space-time. So I think unless these questions are understood and addressed, I just want to point out that, even in the problem of, I think, in this loop quantum gravity, this problem of time itself is a very non-trivial problem. And I think it is one of the stumbling block in the complete understanding of loop quantum gravity. And there are theories like Julian Barbour. I don't know if you have heard of him. Julian Barbour. So yeah, he's a relativist, and he works on, he has some proposals of doing timeless physics. That time can be completely eradicated from the theory. Okay, and one can actually do physics, shape dynamics, and all that. Now, I have of course no clue of what these fellows are talking, but I just want to say that works of Julian Barbour are, they're very respectfully spoken of by people like Lee Smolin and Roger Penrose. So the ideas are very radical, but who knows? And by the way, I mean, there's a trivia about this Julian Barber. It's a, I don't know if you're aware of him. He does physics in a very, like, so after he did his PhD and all that, he didn't want to get into this formal academic system of, becoming a professor and doing research. So he wanted to fund his own research without being, funded by any formal university system, so that he can work in his own way and without any pressures. So it's very interesting that for, I think, more than 3 decades or so, he is completely self-financing himself and doing research. And the way he does it is, he, I think, knows, I think, German and Russian, but I don't know, some other languages. So he translates research papers for earning his bread and butter and stays in some cottage in some, some countryside in UK. And so like he's his own boss. He earns his bread and butter that way and does independent work. So I thought that it's, yeah. And by the way, I think Prati, you showed some interest in this theories of inertia and all that, right? Yeah. So I think in mid 90s there was a major conference on this theories of this Mach principle and its variants. And Julian Barber was one of the organizers, and there is a whole volume of the proceedings of that conference on the Machian theories and their variants, and what is the work done along those lines. So yeah, this is just related to the question that you asked maybe a few lectures ago.
Yeah, maybe you can send me some information by email.
Yeah, sure. He writes actually very well. He has also written books on this, Machian dynamics, and even his own work, Timeless Physics, and all that he writes. And those books are published by Cambridge University. So, and he's being taken very seriously by very respected physicists like Lee Smolin and reporters and Roger Penrose. So I haven't had a really chance to go into his work, but I think when Penrose says that, I think at least maybe worth looking at.
Just one comment: if you happen to write that email, just put it on Sphics Science Center also. Other audience also might be interested.
Sure. Yeah. Sure. I will share whatever I write. The text I will share in the Sphics Science Center.
Yeah. I guess that Mach's principle and this timeless universe, I think these are like related, philosophically related questions, or maybe thought processes. Like we tend to follow the popular stream.
Yes, exactly.
And we completely ignore.
Yeah. These are actually very deep questions. The question of time, and I think it's one of the big impediment in the theories of this along the lines of loop quantum gravity, understanding of time.
Yeah.
Right.
Yeah, that would be interesting, because I wasn't taking off time completely, but I was probably questioning the origin. But
yeah, you should, I think, be interested in this Julian Barber's works.
It will be nice to read. Yeah.
Okay, I think we should call it a day, but I think I like the discussions. But Rathul, thank you very much.
Thank you, Rathul.
You will continue, correct?
That's I guess I was probably telling Shajesh because I mean you were trying to formulate your question and you were not reaching there properly. So
I think Prati's apprehensions are also in place, and Shajesh's approach has also, I think, reasons. So yeah, I mean everything is, it's fine. I mean, understandable, and but the discussion is also important, and the speaker being able to make some headway is also important. So I think it's fine.
I mean, I felt like it is not a kind of lecture, or I should finish it within some duration. I felt
No,
that
that's not the point. The point was like to be able to pose your question. Maybe the strategy should be just pose the question in the beginning itself. So yeah, I don't know. Yeah, I guess like that was the thing, because when Shajesh starts discussing, like it goes into like some high level discussion, and then those who are not just knowing anything about the cosmology or anything, like you guys are using some technical terms, right? Here.
Yeah, that is true.
Yeah, so that's probably the thing I was trying to holding a little bit. Okay, let the question come in and then the details can follow.
Yeah, that is true.
So question then again, Rathul. So we have this, we think of space as expanding or accelerate. So let's talk about the scale constant itself. So we always think of space, the metric in the space, right? The space is dilating in a sense. Can it not be thought of time as contracting, and that's equivalent, completely equivalent?
Time is contracting.
Because it is dt square minus at times dr square, right? I just divide by a of t square completely everywhere and then interpret this as a new time. Is that okay, or probably not okay, is it?
Everywhere means, I mean, you can take the a of t outside and redefine your metric. That is perfectly okay. But then also that a of t is in the bracket, like it is in the.
Then I divide it out by ds square, the total ds that is there.
That's
not allowed.
Is that possible? It's not allowed.
I don't know. I'm just asking.
Because ds square is something, is an invariant, and
yeah. Probably not, right? Yeah, I see.
Yeah.
Okay.
I mean, this metric is valid only in the the frame is called co-moving frame, like that metric is only valid in the co-moving frame. So where, as I said, where the cosmological principle is valid. Okay, suppose you have some kind of frame like moving frame or something, then the metric is different.
Correct. Yeah.
I mean, moving with respect to the co-moving frame. Yeah, I mean, there are papers and there are works where they deal with this kind of frame. Then the cosmology will be entirely different.
But I think to be able to do that, you really need to be able to separate out the space and time part completely, right? And that is not possible unless you frame it in a specific way. Like this canonical gravity, they do it, like, I mean, spoliation of space and time. Separate out the time part. This Hamiltonian formulation of
people
gravity.
do that. It's called ADM formalism. So
yeah, ADM formalism, exactly.
Yeah, people do that. Yes.
It's only in a very specific. You need to first formulate your theory, this Hamiltonian formulation, where you separate out the time and space part.
Yes.
This Arnold-Desser-Wissner formalism, right? I mean, where you separate it out and then you can see the foliation of space and time.
Yeah, that's true. Yeah.
But perhaps in the standard, the metric is very not trivially intertwined in space and time part. So to separate it out there, and then actually the interpretations become quite involved, right? Even in the ADM, when they do it, it's quite actually involved. Actually, it's not as, I mean, I think simplistic understanding of foliation of space and time. I think there are some consequences. It's not like, I think, as intuitive as it appears even there.
Hello.
Yes.
Am I audible?
Yeah, I think there was some disturbance.
Okay. All I'm trying to say is that this separation of space and time is actually, there are very consequences. It's not very.
I mean, this formalism is equivalent to the Lagrangian formalism. So, I mean, this is just looking the same problem in a different way. That's all.
No, it is equivalent, but our hope of retaining our classical picture of things evolving in time, that doesn't quite stay true in that idiom formalism.
I don't know. I have to.
I mean, I also don't know the details, but there are.
But I think
other.
Salesh asked. I don't know. I have to think.
Yeah, mine was very naive. Like I was just thinking in a trivialistic manner. Yeah. But I see what she's pointing out here.
Yeah.
I mean, to be able to do that, one should be able to disentangle the two parts, right? Space and time.
Yeah.
There, I mean, in this co-moving frame, everything is defined, like the time, which is the time measured by the co-moving observer, and the space, which is in the like a of t, a square t times that inside that is actually the co-moving, I mean, the volume inside that bracket, a square t times. Then when you multiply with a square, you get the physical volume. And so these things are already defined and fixed in the co-moving frame. So once you change the metric, then I don't know, maybe if you go to any other frame, maybe we can do, I mean, we can just change the physics from space to time. Maybe it's possible. Yeah. But we have to go to another frame, I guess. Yeah.
It may not be, I mean, given the, I think the signature of the Lorentzian metric, it may not be completely possible to change, to switch between a space perspective and, you have a hyperbolic geometry, right? And
yeah, that is true. It is,
and there is
not always
absolute past and absolute future, right?
So you cannot go from the light cone, like the future, to the other side of the cone. Like, yeah, that is true.
The metric is Lorentzian, so it has a signature, right?
Yeah. You cannot go from time-like to space-like, but you can go from. I mean, yeah. I mean, I have to draw the picture. That there is a light cone. I mean, if you remember, so you can go. You can just go like from one frame to another inside that light cone, but you cannot go outside and go to the space-like region.
Yeah. So in fact, the answer is perhaps there in the very definition of the space-time manifold. That is a four-dimensional topological manifold with time orientation. Right. I mean, it has a time orientation is built into the definition of the space-time manifold.
Yes, that's true.
Maybe we can keep these thoughts open and continue next time. I think that'd be good.
Yes, maybe in the next class, I briefly, explain the same thing whatever I did now, and then I move on to the next session. Is that okay?
Sounds good. Yeah.
I expect some more participants. I will also share some other people and.
Yeah, please. Yeah, I try my best, but I think. Yeah, that will be good. Yeah, if you can. But we'll see. But this was I felt it was good. So at least between us, yeah. But it will be good if we can have a nice audience and everyone starts asking questions. Yeah, that will be really nice.
Yeah.
But slowly we'll reach that. Yeah.
Okay. So the next week or next week?
Yeah, next Saturday. Same time.
Okay. Oh, sorry. I mean, I have a deadline next week, so I will be a little bit busy.
Oh, that's okay. So maybe you can continue 2 weeks down and I can speak
Yeah,
something
that would.
next week.
Yeah,
So
that
I'll
would be
clarify
fine.
that part 2 or the
Okay,
next
that
part
would be.
would be on 2 weeks down the line, right? So 2 weeks
Okay,
from
that
today.
would.
Next week I
Yeah,
will say something.
yeah, that would be fine. Yeah.
Okay, cool. Yeah.
Okay.
Thank you.
Thank you,
Rathul, this
Rathul.
is really nice.
Yeah. Thank you, Sajesh and Prachi. Yeah.
Mm. Yeah.
And
all-
Rishikesh. Yeah.
Thank you.
Yeah,
Thank
all-
you.
all of you
Yeah, it
guys.
was nice. Yeah.
Thank you.
Okay, bye. I
Okay,
end
bye.
everything now.
Bye.
Okay, by Sajesh, you have reached, you are speaking from home?
I am